Perfect. Thank you, everybody. Thanks for coming. Especially we away from Fitzpatrick and the rain. So it's roughly the organization, the structure of the defense locality. So first, wings will do 45 to 50 minutes defense presentation. And then before we close the open committee, we open question for the public. So feel free to ask questions. So if any clarification, maybe a short question, you can raise your hand and ask. So we can do it. But yeah, because of timing, usually we limit the presentation. Thanks, you ready?
Yeah, sure. All right, thanks everyone. Thanks for coming. Today I'll be talking about our work on scalable autonomy for high degree of freedom robots. So what does this, okay.
Yeah, you should.
What is this actually about? We'll be talking about task planning, leg locomotion, and manipulation. So here are some examples of each of these. So in this first task planning example, we have a robot. In this planar scenario, it needs to reach this goal, but before it can pass through these red doors, it has to visit these green regions to pick up keys. We'll be talking about low-level control for leg locomotion. So here, a high degree of freedom robot has to walk over these little stones. And we'll be talking about manipulation. So for example, here the task is for the robot to push the block into this upright position. So if you're not very familiar with robotics, you might be thinking that this is really easy. And why did you spend 6 years on these kind of basic tasks? So to motivate why this is so difficult, let's look at something else, which we can all agree is very hard, which is playing chess. So in chess, there are more possible games than there are atoms in the universe. It's a huge scalability problem. Finding the next move, we all know that really smart people are good at chess, but it's basically been solved. Since the late 90s, when IBM's Deep Blue supercomputer beat the world champion Garry Kasparov, computers have been better than people at chess. And today, if you take your smartphone and go up against Magnus Carlsen, the best player in the world, you'll easily win with your smartphone. But there's something weird going on in this picture if you look at it. So here is our human grandmaster, and here's the seat for the supercomputer. But there's something strange, which is this guy. What's his job? IBM spent millions of dollars developing this supercomputer that could play chess, beating the best human players. But they neglected one little detail, which is just moving the pieces. And here they pulled in some human expert to move the pieces for the computer. And you might think, okay, that was the late 90s. Since then, robotics has advanced a lot. Surely now we have robots that can reliably play chess. But in fact, just last year, we had this story of a chess-playing robot that grabs a child's finger and breaks it in some catastrophic failure. So still, the hardest part of playing chess is actually just moving the pieces. So why do we actually care about this? I mean, why not just let people move the pieces and computers do what computers are good at, like playing chess, deciding what move to make? And there's certainly an argument to be made for that, but there are certain situations in which you would really like to be able to automate basic locomotion, task planning, and manipulation tasks. And just one example of this was after the earthquake and subsequent nuclear meltdown at the Fukushima power plant. So after that natural disaster, there were hundreds of these elderly Japanese retirees who volunteered to go help with the cleanup tasks in these high radiation environments. Basically, they made a cruel sort of calculation. Because they had less time to live, they would voluntarily take on the risks of this high radiation environment and perform these tasks. Now, the tasks that they're performing are not some crazy advanced thing. They didn't need particular advanced degrees. They didn't need amazing strength or athleticism. This was basic task planning, locomotion, and manipulation. So that's what we'll be talking about today. My talk will have three parts. First, we'll talk about task planning with temporal logic. Then we'll talk about how to bridge the gap between the simplified models we use for planning and full order nonlinear dynamics with a more formal approach, and then with a less formal, more flexible approach. Throughout the talk, since there's a lot to get through, I'll try to be light on technical detail and heavier on intuition and results. So first we'll talk about temporal logic task planning. So temporal logic is one way to specify high-level tasks in robotics. It's not the only way, but it's one convenient way. In temporal logic, we have logic, so our basic logical operations, and, or, and not. And we have some time-related operators like always, eventually, and until. And with these operators, we can combine them in interesting ways to make some specifications that we would want our robot to do. So here's a simple example: eventually reach a goal. So now this robot, which is at this point here, is tasked with reaching the goal. We could make it more complicated. We could add an obstacle. So now the specification is eventually reach the goal and always avoid the obstacle. So now we have to go around the obstacle to reach the goal. You can continue building this out. Here we have two intermediate targets in addition to the goal and the obstacle. So we have and eventually reach target 1 or target 2. And you can see how you could build these out to get some interesting behavior. The task that we want to do, given a temporal logic specification, which we use phi, we want to find a path for the robot that satisfies the specification. And turns out you can frame this as a non-convex optimization problem. So here we're saying the signal y satisfies the specification if this function, this rho, which is a scalar value that measures how well you satisfy the specification, is positive. So basically you can pose a simple optimization problem, maximize this. What this can look like, here's a simple specification with two variables. Here's our scalar function rho. You have this cost landscape that often has multiple peaks and sharp edges. So that's a problem for our conventional optimization methods. You would want a smooth surface, and ideally you wouldn't want these sort of multiple peaks because you could get stuck there. So what we did in some earlier work is we proposed a smoothing method. Basically, we can take this function here and under approximate it as this smooth landscape. Now we can do gradient descent or something on this and find a optimum that's a lot better. If we apply a lot of smoothing, you can sometimes get rid of the different peaks, but that's not always possible. And there's no guarantee that your local optimum won't shift or anything. It's not a perfect solution, but it works in practice. And here's some examples. For example, here's a specification reaching one of two targets. We maximize the robustness value subject to dynamics constraints, and we get this nice solution with a standard gradient-based optimizer. In this paper, we extended that to use DDP/LQR to scale to larger, higher dimensional systems. Here's a simple specification reaching one of two spheres. And again, we find that the solution with local optimization. The problem with this approach is these local minima. Oftentimes, you can get stuck in these solutions that are, even though there's a satisfying solution up here, you get stuck down there. And what that can look like in practice is pretty bad. So here's an example with a very bad local minimum. It's a very simple specification, just go around this obstacle to reach the goal, but we are stuck in this local minimum where we're trying to blast through the obstacle, which is clearly not what we want. So what can we do? Fortunately, there are some methods for global optimization. In particular, mixed integer programming is popular for temporal logic specifications. The basic idea is we introduce a bunch of binary variables for each time step and for each subformula, and we can add constraints to ensure that the specification is satisfied. So in our little cartoon picture, this means that we're finding the global optimum. And in this example, we find the path that actually goes around. Great, problem solved. Wonderful, use mixed integer programming, globally optimal solution, and we're done, right? Well, no, because you have exponential complexity. As the number of binary variables increases, the cost of solving a mixed integer program increases exponentially, the worst case cost in case. So we might want to have a very densely sampled path, and as we add more samples to our path, our solve time really blows up in a quite nasty way. So what can we do with this? One approach that we tried to take was to reduce the number of binary variables. So if you reduce the number of binary variables, then you are starting to chip away at that worst case exponential complexity. And what we noticed for temporal logic is that you don't actually need a binary variable for every subformula for every time step. For some types of subformulas, in particular for the conjunctive type subformulas and always, you don't need binary variables at all. You still introduce these indicator variables which take value 0 or 1, but you declare them as continuous for the solver, and then the solver can work a lot more efficiently. For disjunctive type subformulas, like or type things, you need some sort of binary variable. There's like an either or type choice. But you can use some clever tricks from this paper to encode them using fewer binary variables. So the intuition, I'll just give the intuition here. Suppose we have this vector of 8 elements, and we know that exactly one of them needs to be non-zero. The old way would be to have a binary variable in each cell. So you have 8 binary variables, and you say they sum to 1. But you can do a lot better if you just store the index of the non-zero value. So here, the non-zero is in slot 0, 1, 2, 3, 4, 5, and 5 in binary is 1, 0, 1. So we just store these 3 binary variables to encode the same information. And when we do that for our same specification, we get a lot better solve times. So here we're able to, for that same specification, go up to larger number of time steps. That's still not perfect. It doesn't always help. This is kind of a carefully chosen example where you really get a lot of benefit from this. But the mixed integer solvers have a lot of tricks and heuristics. You're not always in the worst case performance scenario. And sometimes actually reducing the number of binary variables makes things worse. To make this problem even worse, this discrete time formulation of temporal logic has some problems. So here's this scenario we saw before where you want to pick up 2 keys before passing through these goals. And if we pass this to our mixed integer solver, this is the solution that it gives us. So it picks up the 2 keys nicely, but then it decides that it's just going to blast through the wall again to get to the goal. And this is not a local minimum like we saw before. Instead, this is exploiting the fact that we're only considering the state at these discrete time steps. And so we can get this pass-through or clipping problem. You can make this a little better by using more time steps, but again, we get into this regime where as the number of time steps increases, you have exponential complexity. So that motivates our latest work using convex optimization to solve temporal logic task planning. So it should be surprising that we can use convex optimization to solve these kind of logical problems. But the reason we can is because we use this graph of convex sets formulation, which is a way to deal with combinatorial problems using convex optimization. And I'll talk a little bit about how that works. So in this case, we have our temporal logic specification, in this case, saying not B until A, and we have a partitioned workspace. So here, a robot is this dot, and this partition is labeled B, and this one is labeled A, and we say don't visit B until you hit A. That's the specification. So what we do to cast this as a convex optimization is we first convert our logical specification into an automaton, which is this graph structure that captures the logical specification. Then we combine this automaton and our partitions into a graph of convex sets. So the actual graph of convex sets that we make is very large, high dimensional, and abstract. This is just a simple example of a graph of convex sets in general. So in a graph of convex sets, you have a graph, it's a directed graph, and each node is associated with this convex set. The goal is to go from this source vertex to a target vertex, and there's a continuous variable inside each set that you want to minimize the length between. So in our case, this graph, the edges come from the automaton and the convex sets come from the partitions. So in that sense, it captures both the logical aspect from the automaton and sort of the physical layout of the scenario from these partitions. Then the continuous variables are control points of a Bezier spline, which we'll see in a minute. So we can consider fully continuous paths. Now, the nice thing about this graph of convex sets, this is an NP-hard problem in general. It can be solved exactly with mixed integer programming. So that doesn't seem better than what we had before. But that mixed integer program has a very tight convex relaxation. And what that means is we can solve it, pretend there are no binary variables, and then do some rounding on those binary variables at the end to get a solution. And it turns out that that seems to work quite well, including for these complicated temporal logic specifications. So here's an example, just this toy example where we have this two Bezier curves and this continuous path that solves the specification. We can add constraints for continuity like here, and we can add constraints for smoothness as well, which we'll see in the next slide. So here's our example that failed before. And now, instead of a discrete time path, we have a continuous spline where we don't deal with this clipping problem anymore. Before we had this problem of exponential scalability in the number of time steps. Here we don't have time steps. It's all continuous. But the closest thing we have to time steps is this number of control points. And if we look at the scalability with respect of to the number of control points, for this example, increasing the number of control points does almost nothing. In general, it's polynomial in the number of control points. So now I have a bunch of examples. This is a randomly generated map where you have to visit partitions labeled A, C, and D, and always avoid those labeled B. And in each of these examples, we're reporting 3 different solve times. The first one is converting the LTL specification to an automaton. And that is a worst case exponential conversion, which you'll see in a minute. Here's constructing the graph of convex sets. That's some inefficient Python code I wrote that could probably be a lot faster. And then finally, what we've put in bold here is a convex optimization time. And the reason we put it in bold is that these other things can be offline. If you know your scenario and your specification, you can compute these offline. Then if you're given a new initial condition, all you have to do is solve the convex optimization problem. Here's a large scale version of picking up keys before going through doors. So here we have 5 doors and 5 keys before we can get to the goal. Again, convex optimization, pretty fast, but you notice that this conversion to an automaton is super, super slow. And so this is this exponential complexity of converting to an automaton biting us. We have looked at using some alternative software to do this conversion, and you can get a lot better. So this half hour could be under 2 seconds if we use better software, but we haven't totally implemented that yet. At some point, you're still going to be bitten by the exponential complexity. It would just be shifted over a little bit. This scales to a high degree of freedom systems as well. So here we have a manipulator arm. It's supposed to reach this target position, which is stretching through the door. Before it can go through the door, it has to press this button. And again, we're able to find a trajectory in under 2 seconds. And our highest dimensional example, this humanoid robot, this specification is saying reach the green, then the red, and then the blue. And again, we're able to get this in under 10 seconds. The worst case complexity with the state dimension is still polynomial. There is some trickiness going on here. So we've welded the base frame in the world so that it looks like it's balancing, but it's not really balancing. This is more like a multiple arm manipulator waving around. So let's talk about some pros and cons here. For temporal logic task planning, I think this is about as good in terms of overall complexity that you can hope for. It's polynomial in the number of control points and the state dimension. It's still exponential in the formula size. But since this is an NP hard problem, I don't think you're going to get away from that. We're still vulnerable to local minima. This is the convex thing is an approximation of a mixed integer program. But oftentimes you get the global optimum. And sometimes when you do, you can certify that it was globally optimal. On the other hand, there's a lot that we're throwing out to do this kind of planning. There's no real sense of system dynamics. For this last balancing example, we're not considering contact. We froze the pelvis in the world frame. There's a lot that we're not considering. So that, yes.
Are you considering the nonlinear kinematics, or are you just doing kind of task planning for the endpoints?
It's all in configuration space. So it's in Q. Yeah, it's not just the endpoints. It's the, yeah. But there's no dynamics, so it's not really nonlinear in that sense. So that motivates our next part, which is using a simplified model to plan, but then having some bridge between these simplified models that we use for planning and the full order system. So in this part, we'll mostly be talking about leg locomotion. And in leg locomotion, we often use simplified models. So here's one simplified model, linear inverted pendulum, with all the mass at one point and this flexible leg. And you might use this as a simplified model for something like this balancer. And most of the time when people use simplified models in leg locomotion, it's sort of an ad hoc way. And what we were trying to do in this work is come up with a more principled way to connect these two. And in particular, the framework that we focused on was approximate simulation. So this approximate simulation framework, the goal is to design some interface, which is basically a controller, such that the output of these two systems remains within some bound. And the output of these systems could be, for example, the center of mass of each of these systems. So I won't go into a lot of detail on how we do this, but just show what it enables, which is, in some cases, we can take constraints on our full order model, like this contact wrench cone constraints that says our foot isn't going to slip, and we project those back through our interface onto the reduced order model. Then, when we're making plans with our reduced order model, we can account for those constraints and ensure that this contact wrench constraints are satisfied on the full model. So here's an example. We compared to a standard whole body controller. First, they get shoved with a 20 Newton push and they both recover. That's great. And next, they get a big shove, 100 Newtons, and the standard controller fails, falls over. But by using this approximate simulation framework, we're able to balance. We then extended that in some later work to humanoid walking. So here's an example of push recovery for a much larger system. Again, our approach is able to withstand the big pushes. We can walk over uneven terrain better than the standard approach. We're also more robust to modeling errors. So here the robot is wrong about each of its link masses. And again, the standard controller falls over. And finally, what might seem like a more simple task, the high center of mass walking is actually pretty tricky because you have these situations where the leg is straight or almost straight. And that tends to provide trouble to most controllers, but ours works pretty well. So this was nice. We were able to get a little bit better performance, some formal guarantees. The formal guarantees that we got were not very strong. We were trying to certify this error bound, but that error bound was pretty generous, like 20 centimeters-ish for this center of mass. It's not that useful. So this got us thinking a little bit more about what are the limitations of this framework? What are the limitations of using reduced order models at all? And one fun thing we were doing to think about this is looking at how cats land on their feet. So a cat has this crazy ability to land on its feet. It's not pushing off of anything. It just does this crazy inertial rotation thing. It's using conservation of angular momentum, changing its distribution of mass as it falls to do this. But if we want to do this on a robot and we look, okay, what reduced order models do we have available to us? Most of them are no good for this task. We have models like the spring-loaded inverted pendulum, which concentrate all the mass at a point. Even richer models like this trunk model have all the mass in one block. So this is going to sort of, these are great for locomotion, but if we want to do a general task that includes this kind of crazy flips, these models are not really gonna work for us. So in a fun project together with Hoa, we did some trajectory optimization using full order dynamics, and we're able to get our quadruped to land on its feet, reorient like a cat. We're nowhere near as good as a cat. We get like a 90-degree rotation instead of a full 180. We have to drop it from the top of this giant ladder. But we're still showing the same principles at play, using the whole body dynamics to land on its feet. So this motivates our final section, which is building a more flexible bridge between our reduced order models, our simplified models that we use for planning, and low-level control. And in particular, we'll talk about trajectory optimization through contact. And this is some work that I started this summer at an internship at TRI. So first, let's consider why bother optimizing through contact in the first place. So we did just whole body trajectory optimization, no contact. We were able to get this crazy cat flipping stuff. That's pretty awesome. But if you look at this video, you can see there's some tricky editing going on. And at the end, it cuts out right before it lands. So if we look at the full video, you can see that it reorients successfully, looks great, ready to land, hits the ground, and bounces up, and then falls over pretty pathetically. So if we're doing trajectory optimization, a lot of robotics tasks involve contact. Making and breaking contact is critical. We might as well optimize through it as well. So in this section, I'll be talking about our custom solver for contact implicit optimization that we've been working on. We did some work using a more standard method to push this ball, for example, but this was very slow. Like this was like several minutes to generate this trajectory offline for just a little simple push. Lots of people have worked on this problem. There are other people developing standard custom solvers. Some people use standard methods like SNOPT, but those general purpose solvers usually aren't reliable enough for this kind of very ill-conditioned problem. Our goal here is not necessarily to make the best contact implicit solver ever, but rather to come up with something that's simple and reliable and allows us to understand what are the real key challenges here. So the approach that we take is inspired by some unpublished work from Todorov, where we take this inverse dynamics least squares approach. So this is a standard optimal control type cost. where we're trying to track some desired joint angles, some desired velocities, minimize generalized forces. Our only decision variables are Q, the joint positions. Everything else we write in terms of Q. And this Q, V, and tau include everything in the workspace. So if the job is to pick up a cup, it includes the state of the cup. And we can't directly apply generalized forces on the cup. So we need an extra constraint, which is to set those generalized forces to 0. Then all the rest of the interesting dynamics are shoved into this term, this generalized force term. This is the inverse dynamics, standard manipulator form. If you're familiar with it, if you're not familiar with it, these are contact forces. That's kind of the tricky part. The rest is nonlinear robot dynamics. So there are a lot of details in our solver. I won't go through all of them, but I'll go through a few key ideas that I think really help. So we take a sparse Gauss-Newton approach to solving this. And so our Hessian looks like this. It has this very nice block pentadiagonal structure, which we can exploit to have efficient linear algebra. Since we take a Gauss-Newton approximation, we only need 3 derivatives of the inverse dynamics. Right now we're getting those with forward differences, which is pretty inefficient, but there are some things you could probably do to do it a lot better. We use then an equality constrained trust region approach. So first I'll talk about the trust region approach. When you're solving a general non-convex optimization, there are 2 basic methods, trust region and line search. Both are well established, very effective, have some theory behind them. Line search is probably the most common. Here's an example. We're trying to find the bottom of this sort of U-shaped bowl. So the optimal solution is down there. And each iteration in line search, we first choose a search direction, might look something like that. And then we backtrack along that to find something that minimizes the cost. So that's the line search. We choose a search direction and then the step size. So the step here would be like that. In trust region, you do the opposite. First, you choose the step size based on how much you trust your model. And then within that trust region, you choose the search direction. And it's not always obvious for which problems either method is going to be better for. So we implemented both and found that a trust region method works a lot better for this type of problem. So here's this little spinner example, which you'll see. This is cost over iterations, and you want it to go down fast. So here, the trust region method is going down a lot faster. Probably with a better line search procedure, you could get this line search line closer to the trust region. But another benefit of our trust region method is that it requires fewer cost evaluations. And in our case, each evaluation of the cost is almost as expensive as a forward simulation of the system. So by minimizing the number of cost evaluations, we can do it a lot better. We need equality constraints. So here's an example. This is our robot, is this little finger with 2 actuated joints, and this is a spinner. It's not actuated. And the goal is to get the little robot hand to flick the spinner. And here's the solution if we try without any equality constraints. The solver thinks it can just apply these imaginary forces on the spinner directly and spin it. So that's not what we're looking for. But if we add these equality constraints, then we get behavior that's much more like we would like, where the finger flicks the spinner. Now I have a bunch of examples. So in all of these examples, we're not specifying the contact sequence at all ahead of time. Here, the goal is just to move the hopper forward like 1 meter. We just say move it forward, and the solver comes up with this cute little hopping motion. Similarly, we have a quadruped. So again, we're not specifying the contact sequence. We just say go forward. And what I think is pretty cool about this is you have this trot-like gait emerges. So if you look at opposite pairs of legs, they move together. And that's a similar gait to what you'd see in various animals in nature. But again, we didn't specify that, anything to hint at that in the cost. This is just falling out of the optimization. Here's an example of a larger humanoid picking something up. these are all, this is local optimization. So the problem with local minima, we still have lots of local minima. So if this ball was over somewhere else, the robot could get stuck, or if its initial guess wasn't really close to the ball, it might not be able to pick the ball up. But even with local optimization, we can still get some pretty interesting behavior. So here's an example of pushing a block. So in this frame, the goal is to rotate it this way. In this frame, there's lower friction with the ground, and the goal is to push it to the side and give it a 45-degree twist. So this is my favorite example, which is a dexterous hand. And the goal is to rotate this ball in various ways. And what you can see that I think is pretty cool, especially in these two, you can see a finger gating pattern emerge. So again, like the quadruped, these opposite pairs work together to rotate the ball. And I wouldn't have known necessarily that was a good way to do the rotation, but the solver finds it. And in this example, which might be harder to see, there is a multi-axis rotation, and the gating pattern is less obvious than this. Another particularly cool thing about this is that we can flip the hand upside down. So there are a lot of amazing, impressive demos from reinforcement learning, other type of approaches that do similar things, but they tend to fail when you flip the hand upside down. In our case, we can flip the hand upside down. This plot here is basically showing that these are, in fact, dynamically feasible. So our solver could allow some imaginary forces on the ball to hold it up, for example. But this plot here is showing this constraint violation. That's basically sum of all the squared imaginary forces at each iteration. And we're driving this to the order of 10 to the minus 4 to the minus 5. So we're good there.
So you're replanning when you flip it, right? You're not.
Oh, yeah, yes. Yeah.
As is machine learning competitor.
Right. So their thing has some advantages over ours. So in our case, we're just finding a trajectory. Like we find one trajectory and that's it. And now we're just playing it back. In an RL context, you're searching for a policy. So you have feedback, and you can start the ball in any given position and it should do the thing. So we're solving a simpler problem, but it's a lot faster. This is on the order of a minute or so from scratch. We think we can get it faster. With the RL stuff, it's working on a compute cluster for weeks, and it's to the point where it's standard practice now to list the tons of carbon dioxide that you've emitted in your training process to rotate the hand. Our ultimate goal is to do MPC with this, and we're not quite there yet. We're still working on making the solver more efficient for MPC. But here's a taste of what that can look like with this little spinner example. Here's an open loop trajectory. The goal is to get to the dot to this other side here, and it looks fine. But when we do this in closed loop with model predictive control, we get this cool emergent behavior where the finger is making and breaking contact to basically adjust the position of that dot to where it wants to be. So a few final thoughts. First, we're really bad at telling what's hard and what's easy. In robotics, some tasks like moving the chess pieces are really hard, and others like finding the best move turn out to be easier. In the section, we talked about approximate simulation, which was a framework for getting strong formal guarantees, but that came with significant trade-offs. For example, we assumed that the foot locations, foot timings, all of that were fixed. And that was necessary to get any kind of formal guarantees. On the other hand, in our last section, doing the falling cat or optimizing through contact, we don't really have any formal guarantees. But the performance that we see in practice is a bit better. And finally, the theme throughout all of this is that by using optimization, we can address scalability challenges. Of course, you need to be careful with that. It's not enough to just pose it as an optimization problem. For example, in the first part with the temporal logic, you can pose an optimization problem, but that doesn't mean it's necessarily solvable efficiently. But if you do some clever things, pose it as convex, or develop some solvers that take advantage of the structure in your problem, then you can start to address these scalability challenges. There are a lot of areas for future research. One of these, which I'd like to highlight, is using contact to address uncertainty. So here's one simple example of a hybrid particle filter. So you could think of this as like a simple system that goes through a contact event at this vertical line. This comes from this paper. And you can see that the uncertainty in this case propagates. After it goes through the contact event, you're more uncertain. But if you're able to detect contact, then you can do some resampling when the true state, that's shown in red, passes the transition and get some better performance. You don't need contact detection to use contact to reduce uncertainty. So here's an example of this pendulum next to a wall. Initially, this sort of fan of pendulums is showing high uncertainty. You don't know which position the real one is. And then so if you're trying to swing it up to the vertical position, you'd have a really hard time. But if you flop it against the wall first, then you sort of collapse all these into one, and you can do a nice swing up that addresses uncertainty. There's a lot of other areas for potential future research. We've really only scratched the surface here. But with that, I think I'll conclude. I'll be happy to take any questions. Thanks to many people, thanks to my committee, thanks to my advisor, Professor Lin, my lab mates, now all of whom are pictured here, everyone in the robotics and control group. Thanks to Aikut and Alejandro at TRI, who have been working with, especially on this last section, doing an internship. There was a great experience. Thanks to funding sources, and finally, thanks to all of you for coming to this.